Today we are going to discuss about temper embrittlement. First, please click on subscribe button to get more learning videos. Temper embrittlement is reduction in toughness due to metallurgical changes. Temper brittlement can occur long-term exposure of metal at temperature of 650 degrees Fahrenheit to 1070 degrees Fahrenheit or 343 degrees Celsius to 577 degrees Celsius. Due to this, during Charpy impact test, ductile to brittle transition temperature shift upward direction. Due to this, equipment may susceptible to brittle fracture during startup and shutdown. We can see in the figure that ductile to brittle temperature shifted to upward direction. Affected material: 2.25 chromium, 1 molybdenum low alloy steel, and high strength low alloy chromium molybdenum and vanadium rotor steel. 2.25 chromium, 1 molybdenum materials manufactured prior to 1972. Alloy steel composition, thermal history, metal temperature and exposure time are critical factors. Alloying elements like manganese and silicon, and the tramp elements phosphorus, tin, antimony, and arsenic are more responsible for temper embrittlement. Temper embrittlement of 2.25 chromium and 1 molybdenum steels develops more quickly at 900 degrees Fahrenheit, 482 degrees Celsius, than in the 800 degrees Fahrenheit to 850 degrees Fahrenheit or 427 degrees Celsius to 440 degrees Celsius range. But the damage is more severe after long-term exposure at 850 degrees Fahrenheit or 440 degrees Celsius.
Affected units or equipment: hydroprocessing units, particularly reactors, hot feed and effluent exchanger components, and hot HP separators, FCC reactors, cooker and visbreaking units. Welds in above-mentioned alloys are often more susceptible than the base metal and should be evaluated. Inspection and monitoring: a common method of monitoring is to install blocks of original heats of the alloy steel material inside the reactor. Samples are periodically removed from these blocks for impact testing to monitor and establish the ductile brittle transition temperature. The test blocks should be strategically located near the top and bottom of the reactor to make sure that the test material is exposed to both inlet and outlet conditions. Process conditions should be monitored to ensure that a proper pressurization sequence is followed to help prevent brittle fracture due to temper embrittlement. Thank you for watching.